So now we're going to go on to compounds that have more than one chiral carbon, such as the one drawn up to my left, which is, or my right, I can't tell, which up in the corner underneath the logo, which is 3-bromo-2-butanol. I also have the model of 3-bromo-2-butanol right here. And we're going to look at the different ways that these two groups can be attached and the different number of stereoisomers involved when you have more than one stereocenter in a molecule. Okay, here's 3-bromo-2-butanol. I've drawn it like this. Let's put the R's and the S's on this compound. So to review, you find your stereocenter, your chiral carbon, and you number according to atomic number. So bromine wins. This is number 2. This carbon is number 3. And the H that's going back is number 4. We don't have to draw it in. We will assume that it's there. So when you look at this compound right here, the carbon with the bromine is going in a clockwise direction. So this will be R. Now I'm going to change my pen color so we don't get these numbers mixed up when we do the OH carbon. Okay, O always beats carbon. Doesn't matter how many things are attached to the carbon, even though the bromine is attached to this carbon, O always beats carbon. So O gets the 1, this carbon gets the 2, and this carbon gets the 3. And again, we have the 4 already going back because we want the 4 to go back. Now, when we look at 1 to 2 to 3, again, this carbon is an R carbon. So the way we would name this, we would put the absolute configuration, the R and the S, out front. So we would say 2R, 3R dash 3-bromo-2-butanol. So if we think about it, we have 2 chiral carbons, and each chiral carbon can go 2 ways. So if you look at the math, there should be 4 possible stereoisomers for this compound. And that comes from, let me finish, stereoisomers. That comes from the fact that you have 2 things taken 2 ways. So 2 to the n, where n is equal to the number of stereocenters or chiral carbons, will be equal to the maximum number of stereoisomers. Now, that doesn't mean you're always going to have 2 to the n stereoisomers. I'm going to add stereo up top because we're going to look at some planes of symmetry. But for this molecule, there will be 4 different stereoisomers. So I've redrawn it again right here, and we're going to find all of those 4 stereoisomers. I'll label this as R, and this is R. And now let's reflect this molecule through a mirror. So here's the mirror, and we're going to draw it just like we would see it on the other side of a mirror. So down, up, down. Let's make sure it looks nice. And then OH on this carbon and Br on this carbon. Now it's good to take this and do what I call a pancake flip, a 180-degree flip. So when I do that, I'm going to go like this. This is my pancake flip. And what happens is the OH goes back and the bromine goes back. Now, why would we want to do this? Well, if you take this molecule right here and move it To look at this one, you'll see that the carbons all line up, but the bromine and the OHs are on opposite sides. I'll move it back. So since these are completely opposite, this would be S, and this should be S. And this will be S, and this will be this. These two are the same compound. These two compounds, let's label this 1 and 2. 1 and 2 are enantiomers. They are non-superimposable mirror images of each other. Now, if I look at a different stereoisomer of 3-bromo-2-butanol, I'll keep the bromine in the same position, but I'll switch the OH around so the OH is going back. Now, if we go through and do R's and S's, of course, this compound or this carbon will be the same. This should be R, and this is opposite, so this is S. Now, these two are not enantiomers of each other, but they are stereoisomers of each other. If we number this 3, 1 and 3 are what we call diastereomers. Diastereomers are stereoisomers that are not enantiomers. There's no overlap between enantiomers and diastereomers. In fact, I misspoke on the last podcast. Diastereomers do not have to have chiral carbons because the kinds of stereoisomers we've already looked at, the cis and trans isomers of the cycloalkanes and the cis and trans isomers of the alkenes, like this, or 2-butene versus cis-2-butene. These are stereoisomers that are not enantiomers. These are also diastereomers. They have no potential to have enantiomers because there are no chiral carbons in this molecule, but they are stereoisomers that are not enantiomers. So if we reflect this molecule, number 3, through a mirror, and do the same thing we did with number 1 and number 2. So we're going to draw it like this, and then the OH will be going back at this position, and the bromine will be coming out. And I'm going to do the same pancake flip here, so I get the carbon chain lined up the same direction as this. As this flips over, the bromine will be going back at this position, and the OH will be coming out. So this will be compound number 4. And so 3 and 4 are another set of enantiomers, or non-superimposable mirror images. And so the relationship between 1 and 3 and 1 and 4 are also diastereomers. So if we look at any compound that has multiple chiral carbons, I'm just going to draw this bicyclic compound here. Now, it is a good thing to go through and make sure you can see the stereocenters in a compound such as. So what you want to look for is a carbon that has 4 different things attached. So this compound carbon right here is a carbon that has 4 different things. Now, at first glance, you'd say, well, that is the same as that. They're both CH2s. But remember, we have to look for overall symmetry and keep marching to the same till the first point of the difference. So this carbon with the OH is different than this carbon over here. So there's no plane of symmetry. So this carbon is chiral, as is this carbon down here. That's also chiral. None of the other carbons in the rings are chiral until you get over to this one with the OH. So drawn flat, you can't tell what stereoisomer it is, but since there are 3 chiral carbons, there are 2 to the third, or 8 possible stereoisomers of this molecule. And remember, each molecule can have only one enantiomer. You can't have more than one non-superimposable mirror image. So when you look at stereoisomers, remember you're looking at sets of enantiomers.